All right, let's dive into a classic kinematics problem from one of the most famous physics books you'll ever find. We're not just going to hunt for an answer today. Oh no. We are going to break down every single step so we really understand the physics behind all the math. Ready? Let's get into it.
This cover. If you've been through a tough physics program, you've probably spent some quality time staring at this thing. Irodov's Problems in General Physics is absolutely legendary for its challenges. They're tough, for sure, but you know what? Solving them is one of the absolute best ways to build a real, rock-solid intuition for how physics actually works.
And today, we've got our sights set on problem 1.20. Our mission here isn't just to race to the finish line and get the answer, but to really truly get the why behind every single move we make. So here's the setup. We're told how a particle's position changes over time. That's its radius vector, r. Just a fancy way of saying its position relative to the origin. Now this equation has two important pieces. A, which is a constant vector, meaning it's got both a size and a direction, and alpha, which is a positive factor, or a scalar, so it's really just a number. The problem asks for two things. What's the particle's velocity, and what's its acceleration? Okay, first things first. Let's track down the velocity. We've got the position as a function of time, so how in the world do we get from position to velocity? Well, it all comes back to one of the most basic fundamental rules of kinematics. Velocity is literally defined as how fast the position is changing. In the language of calculus, that just means it's the time derivative of the position vector. That one little relationship, that's the key to this whole first part.
That's right, we've got to take that position vector r and differentiate it with respect to time, t. So let's actually walk through the calculation together.
Okay, let's break it down. First, for step one, I'm just going to expand that expression for r. It just makes the derivative a little cleaner. We get at minus a alpha t squared. Now for step two, we set up our derivative. And here comes the fun part. Step three, the derivative of at with respect to t is just the constant vector a. Simple. For the second term, we just use the power rule. The derivative of t squared is 2t, so we end up with minus 2a alpha t. And that brings us right to our result in step 4. And if we just tidy that up a little bit, we can factor out that vector a to get our final, clean expression for velocity. So v of t equals a times the quantity 1 minus 2 alpha t. And just like that, part 1 of the problem is solved. See? Not so bad.
So we've got our velocity equation. Now, what about acceleration? Well, if you understood the last part, this is going to feel very familiar. It's pretty much the same exact process, just one step deeper.
Yep, you guessed it. Just like velocity is the derivative of position, acceleration is the time derivative of velocity. It's all about measuring how our velocity is changing from moment to moment. So we're going to take the velocity function we just found and differentiate it one more time. Okay, starting with the velocity we found in step 1, we apply our derivative operator in step 2. Now, have a look at step 3. That first term, the vector a, that's a constant, so its derivative is just 0. It's gone. Easy. Now for the second term, negative 2a alpha t, the derivative with respect to t is simply the constant factor out front, and that gives us our final answer in step 4, just negative 2a alpha. And there you have it. That's our final expression for acceleration. The acceleration vector w is simply a constant. It's negative 2 times the vector a times the scalar alpha. Now hold on a minute. Let's pause and really look at this result. Do you notice what's missing? There's no t anywhere. The time variable has vanished. And what does that mean? It means the acceleration of our particle is constant. It does not change at all, no matter how much time passes. So what does that actually mean for the particle's journey? A constant acceleration should immediately ring a bell. It should make you think of a very specific and very common type of motion. What do you think it is? Okay, this is my favorite part. This is where the magic happens. We're going to take these abstract equations and turn them into a real physical picture that we can actually visualize in our minds. Let's piece this puzzle together. So at time t equals 0, its position is 0. Our particle starts at the origin. Its initial velocity is just the vector a, so it gets an initial kick in that direction. But check out the acceleration. It's constant, and it always points in the direction of negative a. So think about what's happening. The particle is launched in one direction, but it's constantly being pulled back in the exact opposite direction. This is exactly like throwing a ball straight up in the air. It goes up, it slows down, it stops for a split second, and then it comes right back down.
It's motion along a straight line, which is really just a kind of flattened out or degenerate parabola. We can even map out its whole journey. At t = 0, it takes off in the direction of A. Then, at this one very specific moment in time, when t = 1/2 alpha, its velocity hits 0. That's the peak, that's the turning point. For any time after that, the velocity becomes negative and the particle starts moving right back where it came from.
So let's pull back for a moment and really summarize everything we've managed to figure out from this one little equation. And here's the whole story all in one table. We started with the position, we took a derivative to find the velocity, and then we took a second derivative to find that crucial piece of the puzzle, a constant acceleration. Seeing it all laid out like this really drives home how these ideas are connected. And that's really the big picture, isn't it? This problem is a perfect demonstration of the core concepts of kinematics. It beautifully shows that direct, powerful link between position, velocity, and acceleration, all through the simple act of taking derivatives. And most importantly, it reinforces that deep connection between a constant acceleration and, you guessed it, parabolic motion. So, I'll leave you with a final thought to chew on. In our problem, the acceleration was pointed in the exact opposite direction of the initial velocity. But what if it were perpendicular? What if it were always pulling sideways? What kind of path would the particle follow then? Mull that over. Thanks for joining me on this one.